let's continue, not the theorem, now the Jacobian determinant. First, coordinate transformation. Let xi be original coordinates, and suppose we have a transformation. X prime I is equal x prime, attention now, function x1 and x2. This is a particular example where n is equal to. Now this, so here n is equal to x1 and x2, okay? So this is a differential of this variable. Attention, you see, if you recall, if I have f function, for instance, of x and y, this implies that the differential of f is equal partial f respect to x, dx plus partial f respect to y dy. Exactly here, so this is a function f, and this is x1 and x2. You just expand, okay, or this differential here, okay, for each component x prime. So let's erase over here, okay. This is from calculus. Now I can represent these equalities just using the matrix over here. You see, that's a 2 by 2 matrix. This is 2 by 1 column vector, and this is 2 by 1 column vector, column space. Now, this is 2 by 2. Obviously, if I have a function of x1, x2, and xn, this I have a square matrix, in this case, n by n. So this matrix is 2 by 2, you see? Now, the Jacobian, by definition, the Jacobian determinant is defined. You see, let's use the symbol here. J is equal, okay? That's the definition. It's the determinant of this matrix over here. So, this is the scalar quantity. Now, what I want infinitesimal transformations. What's the meaning? What this means? It's x prime I is xi plus delta xi. Remember that xi is a function of x1 and x2, for I is equal 1 and 2. Now, then it's clear that I take the derivative on the left-hand side, on the right-hand side. I just expand and see this, how easy it is. So the derivative with respect to xj over here, xj over here, and xj over here. But the coordinates, they are independent. So the partial derivative, delta xi, so delta xj, this is the conic delta ij. So I just substitute delta ij, and this derivative here leads to this relation over there. So the Jacobian matrix becomes, this is the Jacobian matrix, okay? This is the element of the matrix. This A, example, A11, A in this, A12, A21, and A22. If the elements are Aij, for instance, it's clear that I can use this determinant over here. You see, there's determinant over there, just to the approximation to the infinitesimal transformation. So I just, the Jacobian, the determinant, you just calculate, you obtain this determinant of this square matrix. You see the determinant, you multiply these elements here minus this element over there. It's quite clear. Now, this times this times this is right here, minus this times this is over there. Now, if you expand this, you see, you just keep keep the first order terms, then this will lead to j is equal 1 plus partial of xi, or delta xi plus order of delta x squared. See, for the first order, you just approximating to ignoring this term over here. So this is, in this case, okay, this approximation of the determinant of the Jacobian, you see, on the first order approximation. Conclusion: under infinitesimal transformation, x prime I is xi plus delta xi, attention now, function of x, okay? Then it becomes j is can be approximated to 1 plus this partial derivative respect to xi. Now, this relation is crucial in the proof of Noether theorem, okay? That's important tools to use as we're going to see ahead. Remember that we are deriving the Noether theorem, okay? That is just a tool to continue the derivation of Noether theorem. Would be 17c, okay? This is 17b. Okay, that's it.